Wanted to welcome everyone to the talk today. My name is Steinbach. I'm an engineer at Citus Data, where I work on CitusDB, which is our distributed analytic database. I'm also a committer and PMC member on the Apache Hive project. And before joining Citus Data, I was an engineer at Cloudera, where I was the team lead for the Hive team. And before that, I've also worked at a number of different enterprise software companies, including Informatica, NetApp, and Oracle. So in my 10-year career, I've pretty much focused exclusively on enterprise software. And more specifically, I've almost always been doing something related to databases. And in light of that, what I'm going to say next, I think, is kind of strange. Back when I was in college, I used to think that databases were really boring. And as explanation for that, and as kind of an excuse as to why I developed that opinion, I blame it partially on where I went to school. So I was an undergraduate at MIT from '97 to 2001, and at the time, you couldn't take a database class there. They didn't offer a single one, which is pretty strange considering that at most schools, especially if you're a systems major, you literally have to take a database class to graduate. And the fact that they didn't offer a database class can be partially explained by the fact that out of 100 faculty members and research associates, they had 0 faculty members who specialized in databases. So my conclusion, based on A, the fact that there was no database, and B, the fact that they had no database people on staff, was that they had concluded that databases were a dead topic, and that it wasn't, worth my time. It was like, researching the distant past, and I was only interested in the new future, so I wasn't interested in it. But, as luck would have it, I graduate, and I get a job at Oracle immediately, where I'm in the server technologies department. And I quickly learned that databases are a lot more interesting than I thought they were. And the databases, in fact, are sort of like, they represent the convergence of all of these other, almost, otherwise unrelated systems topics. So they combine operating systems, languages, compilers, networking, all of that stuff together, including algorithms. So, I learned to appreciate databases pretty quickly. And it seems that MIT also learned to appreciate databases because as soon as I left, they brought Mike Stonebreaker and Sam Madden on staff, and they formed a database group. And 3 years later, they finally got a database class. So if I just waited a couple more years to go there, I would have actually been able to learn something about databases instead of having to do it all on my own. So I think it's kind of interesting to ask, what happened? Why did MIT decide, hey, the time is right, we need to go and recruit some people, we need to start doing some database research here, like this is starting to get embarrassing. And I think there are a bunch of different reasons for this. So this was back in 2003. The previous 5 years have been all about the web. And suddenly, there were literally hundreds, if not thousands, of companies that had terabytes and even in some cases petabytes of data that they were collecting. Or if not collecting, at least that they were collecting and then throwing away. But the question became, hey, can we extract some insights from this information? And a lot of people started to realize that, yes, there was a lot of valuable information that they could get out of it. And in turn, this fed into the growth of the first sort of generation of MPP databases. So, this was all based on research that had been done in the 80s, but suddenly, 15, 20 years later, there was now a market for it. And there was also some very interesting new DB research that was coming out right around this time based on columnar storage formats and columnar engines. And also NoSQL began to catch on. And that was all sort of predicated on the notion that you can't scale SQL. So here, let's replace it with this other lower level API in a different storage backend. And maybe we can do some of the same things. And then at the same time, in sort of almost an unrelated way, Google, published 2 papers that revealed their secret sauce, the way that they, were basically generating their giant search index, and the way that they had managed to build, in essence, a warehouse-sized computer out of thousands of individual commodity servers. And people got really excited about that, and that in turn led to Doug Cutting and Mike Caffarella starting the Hadoop project. And for the first time, enterprise companies started to think about building their own warehouse-sized computers for data-intensive computing. So I think it's worth stopping to consider for a minute, really, what does Hadoop provide and why is it popular? And I think at its core, Hadoop is really a storage play. It's about commodity storage, and it's about sort of freeing enterprises from the NAS and SAN mafia, which are pushing this really expensive storage. And instead, you can basically build your own storage infrastructure out of commodity servers. And on average, you can maybe store a terabyte for $1,000, which is much lower than what people had been paying up to that point. And at the same time, it also gives you the ability to scale out. And it can scale out because, and this is the unique thing about Hadoop, sort of the core idea behind it, instead of creating separate islands of compute workers on one side and storage workers on the other that are connected by a network, where the compute workers have to pull the data over this pipe in order to apply computing to it. Instead, it pushed the work over to the storage. So it co-locates the workers on the storage nodes. And then also, I think another important aspect of Hadoop is the flexibility that it provided. And this flexibility sort of, you can think about it if you compare and contrast it to what people have been using up to that point, which was relational database technology. So with a relational database, before you can analyze your data, you first of all have to import it into your database. And before you can import it, you have to decide on a schema. And there's a lot of overhead to this, both in terms of human overhead as well as computational overhead. So in terms of human overhead, typically you have to talk to your data architect. And this guy or woman has to come up with a way of parsing the data and figuring out how to apply a schema to it. And it typically takes a little bit of time because it's an expensive thing to get wrong. Storage in your database is much more expensive than storage elsewhere. You don't want to make a mistake, choose the wrong schema, and then a month or 6 months later find out that it's caused a ripple effect down your entire data pipeline. Hadoop, on the other hand, basically said, look, just pipe your data into HDFS. It can be in any format you want, and we have a set of flexible tools that allow you to write analytic logic to run on top of it. But at the same time, though, Hadoop had a bunch of problems. And these problems, really, like a quick way of summarizing them is, its problems really related to all of the features that relational databases did provide that were missing in Hadoop. So, in some ways, relational databases, they have their issues, but they also provide a lot of good functionality. So for starters, MapReduce is kind of like the assembly language of cluster computing. If you actually have to write application logic in it or analysis logic in it, it's like you're back in the 1960s. It's very brittle. It's very hard to use. It basically means that in order to do analysis, you have to be a programmer, which was OK, because most of the original Hadoop users were programmers, so this felt completely natural to them. But if you were trying to market Hadoop at the time to data analysts who speak SQL, they would look at it and say, forget it. There's no way I'm using this. Another thing was that MapReduce forced you to very tightly couple details, your analysis logic to sort of the underlying physical details of the way that data was laid out on your system. And that's really the benefit of schemas. Schemas are a logical abstraction. In a database, you don't worry about where your information is stored or what the underlying storage format is. Instead, you just worry about what the column names are, what the column types are, things like that. So it's this very clean abstraction that presents or allows you to cleanly decouple those two layers. So in terms of other missing features, there was no optimizer. There were no indexes. There were no views. In Hadoop, you are your own compiler. You are your own optimizer. And initially, people tried to market this as an advantage, like, oh, I can do a much better job. I'm much smarter than the query optimizer in a relational database. I know all of these details about data as it's laid out. I can do a better job. But the fact is, once you've written 3,000 lines of Java code in MapReduce, you quickly lose sight of all of those details. And if you try to explain those to the guy sitting next to you when he inherits the program that you've written, good things are definitely not going to happen. And then finally, besides just relational databases, there's a whole ecosystem of tools that sit on top of relational databases. And these tools speak SQL. That's how they communicate with the underlying database. So I'm talking about things like business intelligence platforms, ETL platforms, and SQL IDEs. And none of these things worked with Hadoop on its own. So a little while after Hadoop was introduced, Facebook got very interested in it. At the time, they had an infrastructure that was based around this sharded MySQL layer. And they had brought on staff probably the biggest and most intense group of MySQL experts in the world. And even with all of that human capital, they still regularly had their MySQL instances catching on fire, on pretty much a daily basis. So they figured, look, this just isn't going to work, especially since the amount of data that we're collecting and analyzing seems to keep doubling every couple of months. So they saw Hadoop as a way of solving this problem, but they also recognized that Hadoop on its own wouldn't solve that problem because the people who actually needed to access this data basically either couldn't or would refuse to use Hadoop. So their solution was to build Hive. And Hive is basically a way of making Hadoop look like a relational database. That was the goal. And most people, when I talk to them and I mention Hive, or when I see people write about Hive, it's always described as a SQL layer for Hadoop. And that's definitely one of the features that it provides. But in my opinion, that's not the most important feature, and it's definitely not the most novel feature. I think the sort of lasting contribution of Hive is going to be the way that it allows you to apply flexible schemas to flat files in any format sitting on HDFS. So I want to talk a little bit more about that. One of the terms that people have come up with to sort of describe the difference between the way schemas are used in a traditional relational database versus the way that they're used in Hive is to say it's a difference between schema on write and schema on read. So schema on write is how it works in a traditional database, meaning that, as I said before you can import your data into the database, you have to figure out what the schema is. And if you get it wrong, you're in a world of pain. In Hadoop and with Hive, the idea is, look, let's just write the data onto the file system, and we will figure out the schema later on. So basically what Hive provides is a metastore where you store details or mappings, which basically say, look, this is the definition of a table. These are the files that the table maps to. And then also it has a separate mapping that says, this table uses the following security, which is a way of saying, this is the format reader or the format parser that I'm going to use to extract row information from the underlying flat files. So by combining basically information about where the data is, along with information about what format the data is in, as well as a pluggable module, basically, that you can use to then read that data, you have this very powerful, very loosely coupled interface. One of the cool things about this is that you can actually project multiple different schemas onto the same data. I can create a table against a file, and Bob can create a table against the same file. His columns can have completely different names, but we're actually looking at the same data. It's also very powerful because it can support basically any file format. In the early days, people were talking about comma-separated value files, JSON, and things like that. But more and more, we're seeing interest in columnar formats. So for example, Facebook implemented RC file. There's now work on an improved version of that called Trevny, and Hortonworks is working on ORC. So really, with Series, what you're talking about is a pluggable storage engine layer. So Hive can benefit from many of the same optimizations that you see in some of these columnar MPP databases. So as good as Hive is, it also has some serious drawbacks. So one of the big drawbacks of Hive is that since it relies on MapReduce as its execution layer, it inherits all of the latency overhead of MapReduce. And this is fine if you're trying to analyze a terabyte of data, running a query against a terabyte of data, because you're not going to notice the overhead of starting up a MapReduce task and collecting the data. But if you're trying to run a very small query, which on something like Postgres or Oracle would complete in a second, it's going to take 30 seconds on Hive because of all the overhead of starting up a job just to look at that tiny sliver of data. And then the other drawback of Hive, and this is kind of almost a little bit ironic, is that since we managed to make Hive look so much like a relational database, people immediately started complaining about that remaining 30% of features that weren't there that they would find in any other database. And that's the thing. A database is more than just a query execution engine. That's why people say it's a relational database management system. It's that management system aspect of it that includes things like support for all of SQL, also cost-based optimizer, all of the literally hundreds of UDFs that you would find in any enterprise-class relational database, security, data types. Right now, Hive supports a lot of data types, but it doesn't support all of the data types in the SQL standard, and people frequently have to sort of fudge and use one data type when they would really rather use another. So we've definitely made a lot of progress towards implementing all of these things, but it's really a Herculean task. At Oracle, when I worked there, they had 500 people just working on the database server, all in building 400. And I think there are probably at any given time maybe 10 to 15 people working on Hive. And granted, it's written in Java, so it's a lot easier to write it quickly, but still, I mean, it's going to take a long time to get to a point where, in terms of features, it compares to something like Oracle or Postgres. So the question is there some better way of basically fixing the problems that we have in Hive while maintaining the flexibility that you get from Hadoop? And up to this point, I think the best way of solving that problem has been to take an MPP database and layer it on top of Hadoop. And in this situation, what's effectively happening is that the MPP database is using Hadoop as its storage layer. It's not, I'm sorry, this seems to have, yeah, it's not pushing work down to the data nodes. Instead, it's pulling data up to the worker nodes in the MPP layer. And the problem with this approach is that you're really violating one of the core tenets of Hadoop, the core tenet that allows Hadoop to scale out horizontally, and that is that instead of saturating the network with pulling data over it, instead we're just going to take work and push the work over the network to where the data sits. So what ends up happening here in a situation like this is that you get an I/O bottleneck in the network layer that connects these two. And that's what basically means that this sort of arrangement will not scale. So then the next question is, how can we make something like this scale? There's definitely an advantage here because we've solved basically the latency response issue. Since we don't use MapReduce and since we're using a purpose-built query engine that's really designed for executing relational operations, it's much more efficient on a per operator basis. We don't have that latency overhead, but we want data locality. Without data locality, we're not going to be able to scale. So the solution is basically to get rid of the MPP worker nodes and take the worker processes that we're running on those nodes and co-locate them on the data nodes. So this way we achieve data locality. We also achieve low latency because we're not relying on MapReduce. And we also get all of the features of a traditional SQL database. So this diagram, I'm pretty proud of this, right? The animation was very slick. I hope everyone liked it. But the problem with this animation, right, is that if you just saw this, you might have the impression, hey, any MPP database can quickly be modified. We can just take the worker processes that we were running on the MPP worker nodes. We're just going to start running them on the data nodes, and everything will be fine. That's not the case, unfortunately. So the issue really here is that when you start building a distributed database, one of the first decisions you have to make is how you're going to lay data out in your storage layer, how you're going to organize it, how you're going to partition it and spread it across the nodes. And once you've made that decision sort of ripples up, and it has an effect on everything else that you do subsequently. It affects how you structure your query compiler and optimizer, because what the optimizer is really trying to do is work around the layout of data on disk. It's trying to figure out a way to minimize the amount of data that has to be transferred between nodes. So in fact, as far as I can tell, all of the MPP databases that have been built up to this point are not based around a layout that's compatible with the way Hadoop stores things on HDFS. They're not based on a block-based architecture, which means that you can't just take these processes and stick them on the data nodes and be good, because basically these local workers, as well as the global query planner, are not block aware. So they're not basically designed to try to minimize traffic between the data nodes. So in order to accomplish this, you really have to start from scratch. So at this point, there are two databases in existence that you can use right now that implement this new architecture where the worker processes are co-located on the data nodes. So CitusDB is one that you can use. Impala from Cloudera is another example. In terms of overall architecture, these two systems are actually very similar. I mean, they both have the core idea of co-locating workers on the data nodes and also of sort of maintaining the flexibility of Hive. I want to provide a little bit more details about this architecture. And since I know CitusDB best, and since I'm also a little bit biased working there, I think I'll use this as an example. So for starters, before a query even comes into the master node, we sync block metadata off of the Hadoop name node. And this is done so that we don't have to do this on a per query basis subsequently, because that would have a latency impact on every query. So we get the block metadata, and this is used by the query planner later on after it gets a query. So subsequently, it receives a query from the user. And you might notice that on the left-hand side, it says Postgres SQL. That's because to build CitusDB, we're building it on top of a foundation of Postgres SQL, which is an open source database that probably many of you have heard of. So once the query is received, our distributed query planner basically analyzes the query, and it plans out an execution plan using what it knows about the layout of blocks on the data nodes. So since it's block aware, it's able to choose a query plan which minimizes traffic between the data nodes. And the sort of decisions that it has to make are, what order should I do the joins in, things like that. And in order to pick an effective plan, it really needs to be block aware at the lowest levels. So next, the query executor basically takes local queries that have been compiled by the distributed query planner, and it parcels these out to all of the data nodes, where the queries are then taken by our processes that sit on each data node. The CitusDB component on each data node is almost completely stock Postgres SQL. And what we're really taking advantage of here in order to make this work is a new feature that was recently introduced into Postgres called foreign data wrappers. When I first learned about foreign data wrappers, I was really excited because I instantly recognized them as being almost identical to Hive SerDes. It's basically a pluggable storage layer for Postgres. And the fact that it's a public API means that we're not hacking Postgres in order to insert our own layer. It means that we can continue, as each new version of Postgres is introduced, to effectively rebase our layer on top of Postgres and then allow our users to benefit from the new features that keep appearing in core Postgres. The interesting thing about foreign data wrappers, though, is that they actually provide functionality above and beyond SerDes. So SerDes are basically just ways of schematizing or pulling row information out of a flat file. But foreign data wrappers also allow you to push filters down to the underlying storage layer, and they also allow you to collect statistics from the underlying data source, which means that this can be then fed back into Postgres's query optimizer, and it allows us to generate better plans. So after the local Postgres instances have finished generating partial result sets, these are then passed back to the master node, which merges the result sets, and finally returns a response to the user. So like most companies today, we're leveraging open source software to build our product. And I want to go into a little bit more detail about why we chose to use the specific pieces of open source software that we did. So using Hadoop at this point is kind of a given. We really think that sort of the future of enterprise storage is HDFS. It's seen massive popularity among enterprise users. And we also think that one nice thing about the Hadoop ecosystem is that since we're leveraging it as a storage layer, if you have data that you would like to analyze with SQL, but which you would also like to analyze with other tools. Let's say in an imperative scripting language like Pig, or perhaps you'd like to use cascading as a data flow programming layer. You also have that option, because we're not forcing you to convert it into our own storage system. We're not forcing you to convert it into our own storage format. It's just data in HDFS. And we also wanted to use PostgreSQL because, quite frankly, it's an excellent piece of software. But more than that, I think we also viewed this as an opportunity to, in effect, combine two different communities. So we wanted to give people who are using Hadoop the opportunity to also benefit from all of the work that's been done in PostgreSQL, to give them the opportunity to use an enterprise class open source database on top of their platform, and we wanted to give PostgreSQL users the opportunity to use Hadoop, to benefit from basically parallelizing their jobs and running them across massive data sets in a scalable fashion. So it's easy for me to make the claim that Postgres is a world-class, enterprise-class database, but I wanted to also back that up with some examples. So the crown jewel of Postgres, if you will, is its query plan optimizer. So I think at this point, you can go and spend maybe a year learning how to write a query optimizer. You can read all of the research papers, and given 6 months, you could probably write your own query plan optimizer. Chances are it will optimize some queries pretty well. Chances are also that it will not consistently do a good job of optimizing all queries. Taking a first iteration of a query optimizer and actually getting it to a point where it consistently does a good job takes a lot of effort, and it's also something of a dark art. At this point, Postgres' cost-based optimizer has been in continuous development for over 10 years. It has literally hundreds of person-years of effort invested in it. And I think it would be completely irrational for us to think that we would be able to do a better job than this. It also has a bunch of nice features that we're able to take advantage of right away. So for one thing, it uses statistics to choose an optimal plan. And an example of this is that it will do both join ordering, and it will also pick the optimal join method given the layout of data on disk. Another interesting thing about it, which is especially important in the context of co-locating these processes on data nodes, is that it's resource aware. You can configure these worker nodes to say, look, you have only 128 megabytes of memory that you can use. And the optimizer will respond to this, and basically, as in this example, it determines that it needs to use an external sort. It can't do the sort in memory. So this allows us basically to make our local Postgres instances into good neighbors. So earlier I mentioned that a database is more than just a query execution engine, and this is something that I love to harp on, especially because I spent so much time working on Hive just implementing all of these little bits and pieces that weren't there. So Postgres out of the box supports over 300 UDFs. I don't know how many UDFs Hive supports right now. I don't remember how many UDFs I've implemented in Hive, but it seems like we're always implementing more UDFs. There are always more UDFs to implement. And we wanted to allow our users to benefit from a large library of UDFs right off the bat, and that's one of the things that we definitely get from Postgres. And besides just UDFs, there are tons of other features of Postgres that our users also can benefit from. So it has a very rich and also extensible type system. As I mentioned earlier, we have foreign data wrappers, which means that both we as well as our users can easily adapt our system to support different data formats. It has industry-strength security, both in terms of authentication as well as authorization. It has a very fine-grained access control system and also supports row-level security. It supports internationalization, which is one of those features that always takes a long time to implement, especially in a database where there's a very tight linkage between data and languages and things like that. And it also has ODBC and JDBC drivers. And I want to make the point that connectivity is more than just about writing an ODBC driver or a JDBC driver, because it turns out that both of those APIs are so broad and so complicated that no ODBC driver or JDBC driver is actually always, totally compliant. So in effect, whenever a third-party tool announces that they have integrated with a database using their ODBC driver, what they really mean is, well, we figured out all of the ways in which their ODBC driver is slightly broken, and we created a profile that allows us to work around it. And that's been one of the problems with Hive. Like, we have an ODBC driver for Hive as well as a JDBC driver, but that doesn't mean that all of the ETL and BI tool vendors could immediately announce support for Hive. Partially because Hive doesn't support full SQL, but also partially because of all of these little idiosyncrasies in terms of drivers. The fact that CitusDB looks like a Postgres database from the outside means that it should not be nearly as hard for all of these third-party vendors to integrate with CitusDB. And finally, there's also this really amazing ecosystem of Postgres SQL extensions. My favorite is PostGIS, which is a geospatial extension, which I think makes Postgres as well as CitusDB particularly interesting to people who are building mobile applications. And a bunch of other extensions as well, including language bindings that allow you to integrate it with things like .NET or Ruby or what have you. And then finally, I want to talk a little bit more about foreign data wrappers. So foreign data wrappers are based on a 10-year-old SQL standard called SQL Med, which is basically support for external data. And I think the original use case that motivated this standard was federated databases. But a really interesting thing happens, though, when you take this idea and you apply it in the context of a distributed database. And also when you apply it in the context of co-locating the workers in a distributed database on other systems. So we've demonstrated CitusDB running on top of HDFS. And we've also demonstrated CitusDB running on top of MongoDB, which is a NoSQL database. So in effect, what we were able to do was graft SQL on top of a distributed NoSQL engine, but maintain the scalability of the underlying SQL engine. And the same thing could be applied to a standard relational database like Oracle, or if you were already running single instances of Postgres, you could use the same thing there. So it's really this very powerful level of indirection that you can do many different things with. So the thesis of this talk is basically that in the last 6 months, we've seen the emergence of what I think is really a new class of analytic databases that is significantly different from the previous generation. And I wanted to sort of summarize what I think defines this new generation. So for starters, these databases support SQL. And it may seem like I'm sort of stating the obvious here, but over, let's say, the last 5 to 10 years, it's become almost conventional wisdom that SQL doesn't scale. That's the whole idea behind NoSQL. And we think that with this architecture, we've demonstrated that SQL does scale. It's just a matter of figuring out how to maintain data locality. Another defining characteristic of this new generation is real-time responsiveness. So that's something that Hive can't provide because of the fact that it relies on MapReduce. And by replacing MapReduce with basically an RDBMS execution engine, we're able to achieve real-time responsiveness, which really changes the way that you interact with the system. It makes interactive queries and interactive exploratory analysis possible, which really allows you to discover things quickly and quickly iterate your logic. And then I think really the big defining characteristic from an architectural perspective of this new generation architecture is that it maintains data locality. And that's the fundamental thing that allows it to scale out. Scale out in the same way that Hadoop does. So I think the previous generation of MPP databases could easily scale to 10 nodes. Perhaps if you pushed hard, you could scale them to 100 nodes. There's no reason why, with our system, you can't scale out to 1,000 nodes. And finally, I think the other defining characteristic is schema on read, which is that level of flexibility that Hive provides and that we maintain. So where are we at? Like I mentioned earlier, you can download and use CitusDB today. Our integration with Hadoop was announced a little over a week ago, and it's in open beta at this point. On our website, we have binary packages for many of the popular Linux distributions, as well as an EC2 AMI that you can use and quickly spin up a CitusDB cluster and kick the tires, if you will. And for more information, I'd recommend you check out a little bit of documentation that we have on our website at the following URL. I also wanted to say that we're hiring. If the stuff that I've described today sounds interesting, if you like hacking on, man, this is bad. If you like hacking on databases, you should really get in touch with us. We would really like to talk to you. Also, we're based in San Francisco, which is always a strong selling point, I've found. So I'll mention that. And without further ado, it's question and answer time. Question. Thank you. So the question is, how well do SQL join operations scale? So right now, we require basically that one of the two tables that's being joined be small enough that we can, in effect, broadcast it to the different nodes. So at that point, there's no data being transferred between nodes. We're working right now on implementing big table joins. Actually, this is Özgun, who's the primary architect of the system. I think he probably wants to jump in here.
So they scale pretty well. And we do, that's the short answer, I would say. And basically, it's when you run a SQL query, there are one of two ways in which we can do distributed joins. If the tables are small enough, we're going to replicate them. If they're partitioned on the same key, we're going to do local optimizations. If they're partitioned on different keys, we're going to repartition one of the tables, or like both of the tables, and then shuffle the data in the system to be able to do the join operation in a scalable manner.
Great.
Question in the back?
You're saying that you're really optimizing from Postgres, but it assumes a certain algorithm of performing basic elementary operations at the lower level, right? But your Hadoop operations behave very differently from what database should expect. How do you resolve that?
So is the question that we're sitting on top of Hadoop nodes, and the Hadoop nodes themselves actually do their own operations, and then there's the PostgreSQL database sitting there doing its own stuff. How do we manage the resource isolation between the two guys, or?
How do you manage the optimization part? How do we reconcile assumption of the query optimizer with the reality of the operations happening on Hadoop node?
So basically what the query optimizer is going to do for us is we're going to tell it this is the amount of resources that you're allowed to use, and then it will collect statistics about the underlying data, PostgreSQL itself, and it's going to execute in that manner. Now, when the other Hadoop nodes are running in the background, obviously there is going to be the resource isolation issue because they're going to be doing their own stuff, and that's something that we're essentially looking into. Particularly Yarn is an interesting feature that's out there that we're going to integrate into.
This is a problem with all of the systems that have been introduced at this point. I mean, I think that right now, the Hadoop platform, basically, people have acknowledged, like the community has acknowledged that resource management is a problem that needs to be solved, which is different than, let's say, 2 years ago where people were like, look, it's just a JVM ecosystem. Everything is a MapReduce job. We don't have to worry about this. But now it's like, look, this is a heterogeneous system. It needs to be able to support many different types of execution engines. So we're actively participating in that discussion, and we think that Yarn is probably one of the ways forward, but we're waiting to see how it develops.
One more question.
Question over here.
So it seems that the runtime performance would depend on making sure there's not that much inter-node data node transfer.
Yeah.
And that in turn is dependent on the state of the data that's available at the master node.
Yes.
But what if that's mutating? That's obviously mutating at runtime.
So
So if you're not current, it seems that you might not be able to completely avoid inter-node data transfer.
So just to repeat the question is that the runtime performance depends on the layout of the data on the data nodes, and the master, the layout on the data nodes can be changing. The master needs to keep up to date with that layout, or the plans that it generates will suffer.
Yeah. And the answer to that question is we're going to synchronize the differences between the HDFS name node at the moment along with the CitusDB master node. I will try to be as current as possible. When there are discrepancies, obviously there's going to be some performance overhead. But the current synchronization mechanism actually can diff the difference between the two metadatas, and then it will synchronize the new metadata over to the CitusDB master node as fast as it can, basically.
We also benefit sort of from the fact here that blocks in HDFS tend to be very large. So in terms of sort of like block metadata updates that you would need to stream from the name node over to the master, it's like a small bit of information in relation to the amount of data that's actually being written in. A question in the front? You'd like us to compare? Okay, I think the question is, have we compared, or would? Oh, so the question is, do we have any benchmarks that we've published comparing CitusDB performance to other systems such as Hive or Greenplum's Hawk?
So we've actually done benchmarks on for Hive. Hawk is recently announced, so we're going to be doing benchmarks against them too. In Hive, our query performance is 4 to 20x faster when the data is in binary format. And we're going to publish more thorough results using the TPCH benchmark, I guess, in the upcoming months.
We also think that there's an important distinction that needs to be made between this new architecture that we're talking about and MPP databases. And that distinction is that we don't do a load operation. We operate on data in place as it lands in HDFS. And MPP databases are going to be able to get better performance in general because they invest a lot of time converting that data from the original format into their optimized internal format. So there's a lot of, I mean, that takes time. There was a very interesting blog post recently that someone wrote comparing Hive's performance to Redshift. And they said, look, Redshift is 40 times faster than Hive. But then buried down in the notes was the fact that it took 17 hours for them to load the data into Redshift. So if you add in the load time, I think Hive works out to be 100 times faster than Redshift. And so it's just sort of, you know, how you look at this.
And you want to be fair. I think you want to be fair. When we publish the results, we're not going to pick short queries that we're going to execute in 100 milliseconds and that's going to take Hive 60 seconds. We want to be fair and we want to be open and for these benchmarks to be repeatable and make sense. I think that's
and another thing that we've noticed about many of the benchmarks that we've seen published recently is that they only provide benchmarks for data sets that can fit in memory. And you're going to get great performance if you can fit your data set in memory because, of course, you're not I/O bound, you're not streaming data off disk. But we think that for most analytic workloads, especially for big data analytic workloads, that's not going to be a major part of the types of queries that you're running. So we think that that's not a very good representation of what's actually happening.
Let's take 2 more questions and then go to the raffle.
Oh yeah, I forgot. Okay, question here. So can you repeat the question?
The question is, how do you deal with operators that are not easily parallelizable, such as median, I'm guessing distinct is another one, that don't lend themselves well to parallelization? And I think in one or two ways. One way is we can come up with not the exact results, but approximations, good enough approximations that are like, say, 98, 99% exact. By using these approximation algorithms, that's like one way. Another way of doing it is being the exact way, that's obviously going to take longer, is repartitioning the data on another dimension and then being able to push the operators to that repartitioned data to get the exact results.
I want to take a question from the back because I think I've been prioritizing people in the front. So back there on the left. Okay, so the question is it open source? And if not, when will we be open sourcing it? So let me put it this way.
It's not open source yet, I guess. That's the...
Not open source yet, but I also want to add a little something there. So it's kind of interesting in the sense that basically 90% of what we have is open source. The foreign data wrappers that we write are open source. The metadata synchronization is open source. And then another important factor is that as far as users are concerned, it looks like Postgres. And typically, I think the reason why companies like open source is not because it's free. In fact, there are lots of examples. I mean, Cloudera, right, has a business model based around people paying for free software or open source software. What people, though, really are buying is a relationship with someone who will support it. And also, there is the perception that open source software doesn't generate lock-in. And I think that the same argument can be made for us because it looks like Postgres, and Postgres is open source. So you're not getting locked in, by writing SQL queries that won't run on anything other than CitusDB. You're writing queries that will run on Postgres, and who knows, 5 years down the road, there probably will be an open source distributed version of Postgres. It could easily be CitusDB. We're based on 9.2 right now. And actually, that's a good question because we've made every effort basically to structure CitusDB in a way that it's cleanly decoupled from core Postgres so that we will be easily able to rebase our proprietary components on each new version of Postgres and allow our users to benefit from the new features that continue to appear in Postgres. And that's really one of our core goals with this system.